Jupiter is the fifth planet from the Sun. The mass of Jupiter is twice that of all other planets in the solar system combined. I'm Larry Ross, Director of Space Programs at NASA's Lewis Research Center in Cleveland, Ohio. And I'm your host for this 9th program of the 13-part series called Journey Through the Solar System. During this program, you'll see the NASA film titled Jupiter Odyssey. It's about the Pioneer 10 spacecraft launched by the Lewis-managed Atlas Centaur. The probe had the nearest approach to the planet on December 3rd, 1973. Today, we have a clearer picture of Jupiter and its moons than is presented in the upcoming film. The reason? The more advanced Voyager spacecraft later flew by the planet. We will look at the Voyager project in another program and learn newer details, such as the current count of 14 moons. This program's older film reports that there are 12 moons. Now let's see that movie, which shows our first good look at Jupiter in 1973.
They used to be called heavenly bodies. Our local star, prime mover of the earthly environment, father of all life. Our almost twin satellite, phasing predictably through the night. Small wonder both were regarded as gods by the ancients. Today we know the moon as a place. Now picture, if you will, a fantastic world where not one, but 12 moons crisscross the sky, 4 of them moving backwards, 4 others the size of small planets. This is Jupiter, largest member by far of the Sun's family, monarch of the outer planets, 1,000 times the size of Earth. In fact, twice as large as all the other planets combined. It is nearly a small star, a second sun, Jupiter, named for the Roman god of gods. To our eyes, it reveals only its dazzling cloud tops, rivers of wild color, and its trademark, the great red spot, a perpetual storm of unknown origin. On Jupiter, day and night are each less than 5 Earth hours long, and a man would weigh 500 pounds. In early 1972, mankind launched Pioneer 10, the first mission to the outer planets, the first to venture out beyond the orbit of Mars, out through the Jupiter system, and eventually out of our solar system completely. The planets of our solar system come in 2 varieties. The inner 4, including Earth, are heavy, rocky cinders. Where the 5th should be, there's only a band of debris, the asteroid belt. Beyond ride the enormous outer 4, the mysterious gas giants. Astronomers have studied them since the time of Galileo. It was he who discovered Jupiter's 4 large moons with his newly perfected telescope. Beautiful ringed Saturn, 3rd of the gas giants, Uranus, rotating on its side, it circles the sun like a fallen gyroscope. And finally, Neptune. One of Neptune's moons, and 1 moon belonging to Uranus, were discovered by this modern Galileo, the late Dr. Gerard Kuiper of the University of Arizona. His backyard in Tucson has flowers, a swimming pool, and a private observatory. Here at Catalina Peak, His studies have produced some of the most outstanding color photographs ever made of Jupiter from the Earth's surface.
This is sort of a typical photograph which shows the red spot of the planet, which is the most prominent feature. This black spot here is the satellite Shadow. It's the satellite Io, which is the nearest of the 4 large satellites of the planet. The satellite itself is here and doesn't show very well contrasted to the planet itself. Now, the first thing you see is, first, of course, that the disk of the planet is elliptical. That is because of its rapid rotation, which is roughly 10 hours. The period is roughly 10 hours. The diameter of this planet is about 10 times the diameter of the Earth, so it is a gigantic planet. The total mass is not, however, 1,000 times. The volume is 1,000 times, but the mass is only about 300 times that of the Earth. So the mean density of this planet is somewhat like the Sun, and that is because it is largely composed of hydrogen. So the composition of this planet is very, very different from the Earth, and very similar, in fact, to the Sun, except the temperature, of course, is much lower than the Sun. And because the temperature is low, you get a chemistry here which is totally different from the Sun. So you have all these interesting colors here, and what we have been doing in recent years is to try to understand both the motions of all these clouds and their composition.
Our odyssey to the outer planets begins here at Cape Kennedy. A good omen under a mock Jupiter sunrise. The ungainly, pregnant guppy delivers a special cargo. The Jupiter Pioneers were built by TRW Systems of Redondo Beach, California, under contract to NASA's Ames Research Center. The project involved some 25 million man-hours of meticulous work by the government, industry, university pioneer team. Each marvelously compact and reliable spacecraft weighs less than 600 pounds, including some 65 pounds of scientific instruments. The 11 onboard sensors include 5 radiation and charged particle detectors, 1 magnetometer, and 3 light measuring devices. 1 for the visible spectrum and 1 for either end of the visible range, the infrared and the ultraviolet. There's also an experiment to look for asteroids and 1 to measure the number of times Pioneer is struck by space dust. All of these devices together use less electricity than one 25-watt bulb. That's energy conservation. 2 other investigations dig out new information about the Jupiter system from ground tracking data. The question arises, what can 65 pounds of spaceborne instruments tell us that Earth's finest facilities can't? For example, the famous Mount Palomar telescope with its 17-foot diameter glass eye. A scientist who uses both Pioneer and Palomar is Dr. Guido Munch of Caltech.
We have used the 200-inch telescope extensively for planetary observations. This is the largest operating telescope that has ever been built. With this telescope, the planet Jupiter appears of the size of a 50-cent piece. The Pioneer infrared experiment will provide a map of the heat emitted by the planet with a 3-inch telescope. But at the distance of closest approach, the planet will cover 1/5 of the sky. And this is the advantage that we get from the 3-inch telescope to the ground base, to the large telescope here. The need to measure the quantity of heat accurately is that all the meteorology, all the motion of the clouds that we see in Jupiter is governed by the amount of heat coming from the inside. And we hope that a real understanding of the meteorology of Jupiter will in fact provide us with a better way to handle our weather problems.
The second day of March, 1972, Pioneer 10 waits for launch atop a new three-stage version of the Atlas Centaur rocket. Later, a sister spacecraft, Pioneer 11, left the pad on its long and chancy voyage to Jupiter and Saturn. It's not easy to break out of the solar system. It requires enough speed to defeat the sun's gravity as well as Earth's gravity. Pioneer streaks away faster than any previous spacecraft, gulping distance at 1,000,000 miles a day, passing the moon in just 11 hours. Still, Jupiter is nearly 2 years away. On the way out past Mars, the experiments are tested and calibrated. Their data add to mankind's understanding of the interplanetary climate of space. The asteroid belt, as some had imagined it. Before Pioneer 10, it was pictured as a region where great boulders grind together, creating a 40,000-mile-per-hour sandstorm. If so, it might have represented a perpetual barrier to outer planet flights. In fact, the pioneers found very little space dust in the asteroid belt. True, there are several thousand asteroids, some as big as Texas, but they should offer no menace to navigation. Pioneer gets its electricity from small onboard atomic heat sources. At 500 million miles, the sun is too weak to power solar cells. The spacecraft spins 5 times a minute for stabilization. On ground command, small thrusters fire to maintain the spin rate and to keep the large dish antenna precisely pointed at the receding Earth. This radio link is a two-way street. A constant stream of information flows back about the health of the Pioneer and its scientific observations. Pioneer is managed and controlled from Ames Research Center located at Mountain View, California, near San Francisco. The Nerve Center is in this building. Pioneer Project Manager Charles F. Hall.
So we're in the mission control area for Pioneer 10, and behind us is the mission control room. Now, right now, they're preparing to send quite a few commands up to the spacecraft, merely to change the attitude of one of the instruments, the operating mode, so that we can look on Jupiter. The interesting feature here is that the round-trip light time, the time to get a message from here up to the spacecraft, and then to get a return answer, is 1.5 hours. So our people in there have to be used to this 1.5 hour delay when they start planning the mission.
Commander R10. R10. We just received the stat clear message. Roger. R10 Commando, verify command stack loaded. Block message number 9. First command, IP Whiskey 2, time 141032.8. Roger, copy. We're enabling message stack this time.
The Pioneers are run by men who send commands from Earth, not by automatic systems on board. This cuts complexity and costs. During encounter, it's busy here. For example, to command just the electronic camera that makes pictures of Jupiter, Pioneer Control transmits some 15,000 commands in just 2 months. In response to these commands, the camera scans Jupiter's turbulent cloud tops as Pioneer spins toward encounter. Because the spacecraft is moving at up to 80,000 miles per hour, and because Jupiter is rotating at 22,000 miles per hour, the scans do not immediately form a pretty picture. They must be decoded and corrected for distortion. First, the scans are built up line by line on a television display. This gives a quick look at the operation of the system and a tantalizing hint of the spectacular pictures buried in the raw data. After the first stage of prettying up, Jupiter's first close-up portrait emerges. Late November 1973, 20 months after launch, Pioneer 10 closes in on Jupiter. Each hour brings the planet 20,000 miles closer. What lies below those inscrutable cloud tops? Could there be life in this maelstrom where pressures may reach 200,000 times Earth's? There are scientists who think that the answer might be yes, that deep in this raging atmosphere of ammonia, marsh gas, and helium, the self-replicating spark may have been struck. One believer is Dr. Carl Sagan of Cornell University.
Jupiter has an atmosphere rich in hydrogen and its compounds, the same kind of atmosphere that the Earth had at the time of the origin of life. So we think that the building blocks of life, at least earthly life, are being produced on Jupiter today, raining down from the skies like manna from heaven. And Jupiter may be a vast planetary laboratory in the chemistry of the origin of life that's been working for about 5 billion years. It's by no means out of the question that there are forms of life in the clouds of Jupiter. And indeed, if you viewed the solar system from afar, I think you could make an argument that life on Jupiter was more likely than life anywhere else, including on the Earth.
Dr. Sagan also provided for Pioneer the famous picture postcard to extraterrestrial life.
But in the remote contingency that there are interstellar spacefaring societies which might someday pick up this derelict no longer radioing, we thought we would put a message on it to indicate a little bit of where we are, when we are, and who we are. We think that the information on where we are and when we are, indicated in this part of the message by the configuration of certain cosmic objects called pulsars, will be completely obvious to any society capable of traveling between the stars. These two objects will be more mysterious because it is unlikely that there will be human beings anywhere else, even though there may be other creatures elsewhere. And the plaque has served a very useful purpose in making us think about what sort of impression we might wish to give to the cosmos.
Each morning, the key scientific investigators and the key spacecraft personnel meet in the office of Pioneer Project Manager Charlie Hall for a stand-up meeting. Why not a sit-down meeting? Because, says Charlie, people don't talk so long when their feet get tired.
So like a contrast, I can submit over to...
I have the impression that it is all in the text. I don't know for sure that it is all in the text.
With such accuracy, but just grossly, whether we can trust the angles on the
I'm afraid to say anything because I don't know. We'll have to get to...
Say 250 degrees or something like that, system 3, which is not far from what the radio astronomers preferred.
We have 3 sets of accurate observations with the IPP this week since the last precession maneuver.
What we're seeing here is that for both electrons and protons, we're seeing in first approximation an in-phase change.
But don't you know,
you're not...
No, it's all right. Going in pretty consistent. Yeah.
December 2nd, 1973. Tomorrow, Pioneer will make its closest pass of Jupiter, when this fantastic world will fill 1/5 of the sky. Today, Pioneer is being cooked by incredibly severe radiation, yet everything continues to work perfectly. This spectacular picture shows the shadow of the satellite Io, just as Dr. Kuiper's ground-based photo did. But from this distance, new details in the cloud bands become evident. Huge coiling storm areas larger than the Earth. Since launch, Pioneer has been slowing down. Now the pull of Jupiter's gravity speeds it up to a fantastic 82,000 miles per hour. In effect, this crack-the-whip left turn gives Pioneer another rocket stage to fling it out of the solar system. Unexpectedly, the space dust count soars, 100 times as many hits. Jupiter's gravity may act as a cosmic vacuum cleaner. December 3rd. Pioneer sweeps to within 81,000 miles of the cloud tops. Now things happen fast. 15 minutes after closest approach, the spacecraft is targeted to pass out of Earth's sight behind the orange moon Io for a critical 2 minutes. This ultra-precise maneuver will use radio effects to reveal new information about Io, if the signal can be picked up again on the other side, and if Pioneer will obey commands again. Back at Mission Control, there's a maternity hospital atmosphere. They won't know what happened in space until 45 minutes later. The speed of light is much too slow for the anxious parents.
What kind of an illustration do you want to have? What kind of
Future missions. We have observed the planet in the infrared. We've observed the planet in the ultraviolet. It required the actual probing of the atmosphere.
What did go behind you? Oh, we lost it? Yeah, we went out of lock and we were less than 1 second from the plane.
And they're back, you're not back on.
No. Oh, that's an extra trajectory.
5. I'll give you the time in a second.
Well, we missed the EO occultation by 1 second, and I was just sort of kidding him or telling him that you have to go through the ecliptic at the right time. When the EO goes in front of you, we're 3 Jupiter radii away, EO 6 Jupiter radii. You got to get all this thing lined up, and we missed it by a second. Next time we'll do better.
An hour later, Pioneer passes out of sight of both Earth and Sun, this time behind Jupiter. The spacecraft is collecting its worst radiation exposure now. Tension is even greater this time. And so is the relief.
Mark 10 option.
Now Pioneer views a sight never before seen by man, the crescent Jupiter. From Earth, we can see only its full phase, like a full moon. These lighting angles give scientists new information. On the television system, the images rapidly become smaller. Now, several consecutive pictures can be stored on the tube at once. Thanks to energy literally stolen from Jupiter, Pioneer 10 departs more than twice as fast as it arrived.
Early this morning,
Now the world wants to know, what have we learned? The scientists readily admit to newsmen that for each question answered, 100 new ones have been raised.
2 different phenomena going on.
Project scientist Dr. John Wolfe reports.
Approximately 44 Jovian radii. We had the indication of very strange plasma distribution.
We're taking back with us to our laboratories data which essentially are puzzling to us and will take a long time to work out.
Some points are clear. The whole Jupiter system is heavier than we thought, by about the weight of 2 Earth moons.
Our most important finding to date
Io has a thin atmosphere. Thus, Jupiter's 4 large moons probably all have atmospheres.
Seeing relatively abrupt decreases in the field magnitude to much lower values.
A compass on Jupiter would point to the South Pole instead of the North Pole.
Through the magnetosphere.
Experiment.
The infrared experiment successfully mapped Jupiter's heat in fine detail. The planet gives off more than twice as much heat as it receives from the sun. Why? Possibly its enormous gravity makes it contract like a slow-motion star. The white belts are cooler, and therefore higher bands of clouds stretched around basically darker-colored material below. Also, the night side and the day side appear the same temperature. Discoveries like these flash out to the world. To experimenters, some of the most interesting findings concern Jupiter's radiation belts and magnetic field. Pioneer first broke into the magnetic field an incredible 4 million miles in front of the planet. Because of the pressure of the solar wind, this field streams out much farther behind Jupiter. Closer in, Pioneer indicates that Jupiter's intense radiation belts wobble up and down around a magnetic center some 10,000 miles from the center of the planet. In brief, Jupiter is much different from Earth and much more complex than researchers imagined. However, Pioneer proved that a spacecraft could survive the radiation. After encounter, The data tapes for the imaging experiment go to the University of Arizona for computer enhancement. In a meticulous process, millions of data points are juggled up and down the scale. And what emerges is a portrait of Jupiter to challenge the most imaginative artist. The pioneers, first to brave this land of giants, first to fly forever among the lonely and endless stars of our galaxy, carry mankind's message. We're on our way.
Theory holds that Jupiter is so big and so far from the Sun that the huge planet retains most of the material from which it was formed about 4.5 billion years ago. Scientists think that beneath the clouds, Jupiter is an ocean of mostly liquid hydrogen. Theory says that above the ocean is a 600-mile-high, mostly hydrogen atmosphere. Jovian clouds also contain water, ammonia, and methane. Between very cold cloud tops and the very hot interior are probably regions of Earth normal temperatures. Jupiter's lightning could be a catalyst in the formation of organic compounds in these regions. During our next program, Jupiter, a clearer picture, we will see how NASA plans to send the Galileo mission to Jupiter in 1986. Galileo, launched from a shuttle by the Lewis-managed Centaur, will orbit the planet and send a probe into the clouds. We will also see the very sharp pictures which Voyager showed us of Jupiter and its moons. This is Larry Ross saying goodbye from NASA's Lewis Research Center in Cleveland, Ohio. During this program, we are going to see beautiful pictures of the largest planet in our solar system, Jupiter. We will also see some of its 14 known moons in surprising detail. These pictures are better than the Pioneer spacecraft pictures of Jupiter we saw during the previous program. I'm Larry Ross, Director of Space Programs at NASA's Lewis Research Center in Cleveland, Ohio, and I'm your host for this 10th program in our series of 13 called Journey Through the Solar System. Now, let's see a videotape made after the Voyager 1 spacecraft had its closest encounter with Jupiter in 1979. Rodney Mills of NASA describes the Voyager pictures.
This is an image of Jupiter we obtained from a distance of something like 50 million miles, but we were immediately struck by the fact that it looked somewhat different than it did when an earlier spacecraft, the Pioneer, flew by in about 1973 and 1974.
In what respect? The bands? Or?
The bands and the zones look different. The appearance of the Great Red Spot looked different, and a number of other features.
So it's very dynamic.
It's a very dynamic place, yes.
Is it solid?
Jupiter may have a small solid core about the size of the Earth, but for the most part, it's a large bag of liquid and gas, mostly hydrogen. Now, we don't ever see the solid surface. All we see are the cloud decks. We don't know what gives them the color. We have some suspicions, and maybe some of our data will reveal that.
In the years ahead, we have a mission that will take a satellite to Jupiter and penetrate these gases, do we not?
That's right. We have a mission on the books right now which will include a probe that will go down and penetrate into the surface and actually into the surface of the clouds and actually take some measurements.
That'll be exciting. What are some of the others that you have?
Well, I think this is one of the more beautiful of the photographs showing two of the satellites passing in front of the planet. Now, Jupiter has about 13 satellites or moons. Of these, 4 of them are very large. They're the ones which Galileo discovered. And in this photograph, you can see 2 of those moons passing in front of, between the spacecraft and Jupiter.
How about the sizes?
The satellites
are they like
are large. They're large. Actually, 2 of them are larger than the planet Mercury. The 4 Galilean satellites are Io, the one closest to the planet, then comes Europa, then Ganymede, then Callisto. 2 of those are larger than Mercury. 3 of them are larger than our own moon. So they're all really planets in their own rights. What we have out there at Jupiter is really a miniature solar system. We have a large body which is radiating more heat than it receives.
Possibly another sun.
It's a sun that didn't quite make it. Right. But and the density of these satellites varies considerably, just like the densities of our own planets vary. Yes, the ones closest to the central body are hard rocky objects, and the ones further away are less dense. This is a close-up view of shows the great red spot. This is a feature that anyone who has a small telescope can possibly identify on Jupiter. Galileo observed the great red spot. So we know it's been in existence something like 300 years. Now, it moves around the planet a little bit, but it never loses its identity completely. And this is amazing, considering it's really just a storm and a cloud formation.
That's large, too, as I recall, about the size of 3 diameters of the Earth.
It's as wide as 3 diameters of Earth, so it's a large storm. Now, we were very interested in where the energy comes to make this thing exist, and we were interested whether it was rotating or not, and we have found that out. We have found, for instance, that it rotates once every 6 days. I should mention also that Jupiter has a lot of energy. It spins on its axis so that a day on Jupiter is only 10 hours long.
Aesthetically, the photographs are beautiful.
Let me show you some examples of the art, beautiful arty photography that's come out of the mission so far. This is a view of a portion of the planet Jupiter in its normal color. Now, as an aid to trace the flow of the atmosphere, we introduce some artificial coloring, and it comes out very remarkable. This is an example.
We're then going to learn a lot about the dynamics of motion and the flow patterns.
In fact, we photographed the planet Jupiter continuously over a period of a month with still photos, and now we've assembled them into a movie which we can run and speed up the motion, and you can actually see the flow of the atmosphere and the appearance and disappearance of clouds, and our scientists are busily engaged in analyzing that.
It certainly looks different than anything we've seen at any of the other planets. What else do you have here?
Well, before I leave it, let me show you a spread out map of the entire planet Jupiter. This is a new result that's just released this week. This is the equivalent of a Mercator projection. It shows all sides of Jupiter at one time, and it's unusual in that most of us didn't realize how many various plumes and spots there are on the planet, and all of these things move in the movie that I spoke about.
Do they all go at different speeds relative?
Yes, they go, in fact, tend to go in opposite directions. Some of the bands flow one direction, like eastward, and some flow westward. And
lots of questions.
Yes, lots of questions.
And some of the dark spots we had seen and some of the white spots we had seen prior to the...
Some of the white spots down in the southern latitudes have been observed for around 30 or 40 years. I mentioned that the great red spot has been observed for 300 years. Some of the features appear in a matter of a few days or a few weeks, and then they disappear. Yeah. To go on, there were several other features that I should mention about Jupiter. We made a remarkable discovery, and we found that there is a ring around Jupiter.
I understand that.
Right. Now we know that, of course, Saturn has these beautiful silvery rings, and a short period of time ago we found that Uranus has some thin rings, and now Jupiter has joined the club, so it leaves Earth out almost. This illustrates where the camera was aimed. We took a single exposure out in this area where the little square is located at the time we crossed the equatorial plane of Jupiter with the spacecraft. And we took a single 10-minute exposure, and I'll show you the resultant photograph. This is a black and white photograph, and it takes a little explanation. These strange wiggly marks up here are actually images of stars, because the spacecraft was moving during the 10 minutes, so the stars actually left little jagged traces. But in the central portion of the photograph, you'll see these straight lines. Actually, there's 6 separate images. That's right, yeah. And that's the edge of the ring looking straight on at it. Yeah. Now, the ring is very dark. It's fairly thin, probably not thicker than 20 miles or something like that. It's composed, we think, of rocks, and they're very dark. But we'll be taking more images of this with Voyager 2.
Yes, now that you know it's there.
Now that we know it's there, right.
More directly.
Right. And since we discovered it, I believe there has been an observatory here on Earth that has also confirmed the discovery. This photograph of Jupiter has had a ring drawn on it by an artist to give you some idea of the size of the ring. But although we know approximately its thickness, we really don't know the extent of it inwards towards the planet. And we will be measuring that with the next spacecraft.
Are these rings always in the equatorial plane of the planet?
Yes, right. That's, in fact, that's a requirement almost.
Possibly something that never was quite formed into what it should have been into another satellite? Or
it could be the broken up debris of a small satellite, and that's probably likely. There is another object that's fairly close to the planet Jupiter. This is the small satellite Amalthea. It's really not one of the Galilean satellites, but it's the innermost satellite. And this had never been seen by mankind before as anything other than a point of light. In fact, very few astronomers had ever seen it. It's really a small rocky object. It's not spherical in shape. Its approximate size is like 80 by 150 miles. It's very dark, very red. It may be just a captured asteroid.
Traveling pretty rapidly, probably, too, because it's close to the planet.
As the spacecraft swung behind the planet Jupiter, we took occasion to take some images of the dark side of the planet, and we made another remarkable discovery. This is a photograph. It appears rather noisy, but in fact it contains quite a bit of information. This light arc across the top here is actually an aurora display, like the northern lights here on Earth. Right. The atmosphere is being excited by charged particles spiraling in. Then down lower in the photograph there are some bright white spots, and we believe that's evidence of lightning. Lightning above the cloud tops.
Is that right?
The same sort of thing is seen sometimes here on Earth down in the tropical areas, and they're called superbolts. It's a great deal of energy. And these measurements were later confirmed by our spacecraft. We have on the spacecraft an instrument to listen to the planet, and we heard electrical waves corresponding to whistlers, which are created by lightning.
What about some of the other satellites?
Let me speak about the satellites, not exactly in the order we observed them, but the outermost of the 4 large satellites is Callisto. Now, Callisto is not very dense. We know that it has a density that not about halfway between water and rock, so we know that it must be composed about half of ice. It's rather a cold object. It has no atmosphere. This is a color photograph we obtained of Callisto as we flew by it, and we were immediately struck by the fact it's heavily cratered, probably more heavily than the moon is even. And this is evidence that it's not changed much in the last 4 to 6 billion years.
No atmosphere.
No atmosphere. There's apparently no volcanic action, and it's stayed frozen.
It has rings, or appears this.
Right. There is one large impact basin up there where it looks like some very large object had struck it and formed concentric rings around the basin, and those have been apparently frozen in the ice. So it's. And elsewhere you can see some small craters that are very light appearing. It looks like the dark covering on the planet has been thrown aside, and it's exposing probably ice.
Newer ones, possibly, newer craters?
Well, we think probably it was cratered at about the same time in history that the Earth and the Moon and Mercury were, and that was back in way before our time, probably 4 to 6 billion years ago. But it hasn't changed much since then. This is another photograph in color of the entire planet, Callisto. Actually, it's a satellite, but it really deserves to be considered as a planet. And finally, a third photograph of Callisto, which shows in black and white a little more of the cratering detail. You can see
it has been impacted.
It's pockmarked a wide range of sizes. Also, if you notice along the limb or the outer edge of the satellite here, you'll notice there isn't much relief. Apparently, there are no mountains, and that's consistent with the theory that there's a lot of ice in the satellite, and it really couldn't support mountains. Next, moving inward, I'll talk a little about Ganymede, which is probably one of our favorite satellites because it has such a diversity of appearance. Again, here's a full image of Ganymede. You can see it's a different color and has a different texture. There are light areas and there are dark areas. We think the dark areas are a little bit older and the light areas are a little newer. There's some evidence here that the surface has been under a lot of stress and it has been altered during the eons of time since it was formed. There are a fair number of craters, but not as many as on Callisto.
This would be dense, now more dense than what we had seen before.
Right.
More rock, possibly.
A little more rock, but still an appreciable amount of ice and water, of course, if it were warm enough, but it isn't.
Right.
This black and white photograph illustrates the rough texture we see on portions of Ganymede. This looks a little bit like some dune buggies who've been running around in the sand. Actually, the scale is quite a bit larger, and either the surface has been compressed or stretched and given rise to all these ridges.
And we have impacts as we see there.
Yes, so you can see that whenever that happened, it was still before the end of the cratering action took place. Our geologists are having lots of fun with these images. One more rather remarkable photograph here of an area showing both the light and dark surfaces, and we have an example here of a fault line. It's the only place besides the Earth we've seen any evidence of earthquake fault lines. I'll try to point it out down here. You'll see a displacement down in this region of the lighter area where
been moved from
it's been
moved to the left, the whole
right.
So fault lines here. We've not seen this any other place?
No, not on the Moon nor Mercury, and of course, not on Mars. Of course, we haven't seen the actual solid surface of Venus, but so far, this is the only other place in the solar system. Now, moving into the next satellite. This is an image of Europa. Now, this is a rocky satellite. This is actually the best photograph we obtained with Voyager 1. It didn't come very close to Europa. We'll do much better with Voyager 2. Our pictures will be about 10 times larger with Voyager 2. But there's a very interesting feature here on this satellite. You see these long, straight lines down in the southern hemisphere? We don't know what they are. They could be just surface markings, or they could actually be crevices, long, huge canyons. If they are, they're much greater than our own Grand Canyon. They stretch thousands of kilometers.
What's the size of the planet itself?
This again is it's smaller than the Earth, but it's comparable to the Moon.
So we're looking at tracks there, or whatever they are, lines that are a quarter the distance on the surface, or more even, in some cases.
So we're looking forward to the next trip by this satellite.
Io is a pretty interesting satellite.
We have some people with remarkable imaginations, but none of them had imaginations good enough to expect what we found on Io. It's a very remarkable object in the solar system. This is a color photograph showing it has a very goldish, reddish color with some white areas. Now, we expected Io to be a little different, and we expected it to have some salt flats on it, and I think it does. But one of the first things we noticed is there seems to be no evidence of cratering. These other bodies have all shown craters from impacts, and so why shouldn't Io? Well, we thought maybe as we got closer we'd find more, but we didn't. We should have been suspicious of a few of the other features. This rather strange-looking ring feature here about in the center doesn't look like the sort of thing you find on the usual satellite.
That's not an impact? Or
No, it is not.
We don't know what it is.
We do now.
Oh, we do now.
Didn't
all right.
know at the time.
We didn't know at the time.
First saw the photograph coming back from the spacecraft.
I see.
As we got a little closer to the satellite, we saw images like this. Now, this was evidence of lava flow. It looks like a collapsed caldera and a very thin spreading of the dark material, which was thought to be lava. It wasn't until several days after we had gone by Io that one of the lady engineers on our navigation team was working with some of the photographs, and she was trying to fit the circle of Io into a computer program, and it wouldn't fit because it had a funny looking bump on one side of it. You can see if you look very closely down here, a strange looking bump. Well, it turned out that was not an artifact of the imaging system, that was real. So we finally concluded, hey, we have a volcano, an active volcano.
An active volcano.
Spouting out as we flew by. And not only was there one, but if you look at this other bright spot in the image here, you can see something is spouting up there. See, that's a portion of the satellite that's in the shade, or the dark side. Right. But the material's actually being ejected high enough so it's catching the sunlight. There's no atmosphere on Io, so any material coming out of a volcano tends to follow a ballistic trajectory, and it falls back to the surface. And the height of these plumes is something like 150 miles. A lot of material coming out. So suddenly we understood why the surface didn't have any craters.
Yes.
They're all covered up. Apparently this has been going on for billions of years. Yes. At the present time now, we have identified 7 active volcanoes which were erupting during the few days that we flew by it. Now, you couldn't see anything like that if you flew by Earth. Volcanoes just don't go off that frequently here. I have several other photographs that demonstrate this a little more clearly. Here is a spout on the limb of the planet, and again you can see the big fountain of material. Now, we have pretty strong evidence that there's a great deal of sulfur coming out of these volcanoes, and that's covering the surface with sulfur, and a fair amount of it is also getting into the magnetosphere and leaving the satellite. There's another photograph of another volcano here. You can actually see the dark material coming and spouting out. And finally, a color version, a rather famous photograph showing an eruption right on the limb of the satellite. It's approximately in true color. Now, for scientific purposes, sometimes we enhance these photographs, and this is a composite photograph that includes some ultraviolet measurements, and you can see up here the eruption, and it enables us to determine the particle size coming out of the vent. So Io, I think, is nominated as the most remarkable object in the solar system. It's a very active volcanic object, and it's probably been going on for billions of years, and the surface is fresh, it's new, it's continually changing day by day.
Here at the Lewis Research Center in Cleveland, Ohio, we are directing work on modification of the Centaur rocket for use with the shuttle. Centaur will be used to launch the Galileo probe to Jupiter in 1986. Centaur will be carried into low Earth orbit. The rocket will be released from the shuttle, moved to a safe distance, and fired, sending Galileo to Jupiter. During the upcoming Galileo mission, we hope to learn quite a bit more about Jupiter and its atmosphere. Let's go to a film called Galileo Mission to Jupiter, which outlines the project.
The spacecraft carries a parachute-equipped probe targeted for deployment into Jupiter's turbulent atmosphere. The probe will allow our first direct sampling of the Jovian atmosphere and is a forerunner of future probes designed to explore the Sun, Saturn, and satellites like Titan with considerable atmospheres. The probe will descend into Jupiter to analyze and directly sample its atmosphere, believed to be original material from which the solar system formed 4.6 billion years ago. The Galileo mission, named for the Italian astronomer who discovered Jupiter's 4 large satellites, has been designed to use the gravity of those moons to bend the spacecraft flight path during its 24-month tour of the Jovian system. As the probe samples the Jovian atmosphere, scientific results will be relayed to the orbiter for 1 hour before the probe signal is lost at pressures of 10 to 20 Earth atmospheres. Galileo makes a close flyby of Io to study the moon's volcanic surface. Io's gravity in turn bends the trajectory of the spacecraft, helping to send it into orbit around Jupiter. Flying just 1,000 kilometers above the surface, images of the moon show features as small as 50 meters. After relaying probe science data to Earth, the spacecraft will orbit Jupiter at least 11 times, making a close flyby of one of the Galilean satellites on each orbit, yielding high-resolution images and detailed measurements of their surfaces, gravity, and magnetic fields. As the orbit rotates about Jupiter, the spacecraft will sample all regions of the planet's vast magnetic field. The first full orbit of Jupiter brings Galileo to its first encounter with Ganymede. The gravitational effect of the close equatorial flyby reduces the length of the spacecraft's orbit from 200 to 90 days. Using photographic data from Voyager, this computer-simulated flyby of Ganymede shows Galileo's view of the icy moon. Galileo will fly even closer to Ganymede in its second encounter with the moon. Each satellite flyby modifies Galileo's orbit, sending the spacecraft on to its next encounter. Each flyby is 20 to 100 times closer than the Voyager encounters. The Voyager saw only the equatorial regions of these icy moons, but Galileo will photograph the North Pole of Ganymede, providing a new perspective in the study of these large satellites. A flyby of Callisto occurs on the 6th orbit of Jupiter. The ancient, cratered terrain of Callisto is closely studied as Galileo passes over the southern hemisphere of the outermost Galilean satellite. The spacecraft will sweep within 200 kilometers of the surface of Europa at the end of its 8th revolution about Jupiter. Galileo's Europa encounters will give us our first detailed look at this moon's mysteriously fractured surface seen by other spacecraft no better than we see Earth's moon through a small telescope. During its 20-month mission, Galileo will expand our knowledge of Jupiter and its satellites, revealing in detail the bodies and workings of this miniature solar system.
Through the years, we will learn more and more about the universe in which we live. Galileo is just the beginning of what is possible. This is Larry Ross saying goodbye from the NASA Lewis Research Center in Cleveland, Ohio, until next time, when we will travel to the next planet out from Jupiter, the great ringed planet Saturn.